All right, let's take a look at this review problem where we're going to translate these statements into logical propositions and then find the negation. First, x is less than 4 or x is equal to 4. Clearly, that's going to be x is less than 4 or x is equal to 4. So that's the original statement. The negation will be that x is greater than or equal to 4 and x is not equal to 4. And clearly, if x is greater than or equal to 4, but not equal to 4, that means x is greater than 4. But just strictly using De Morgan's laws, that would be the negation. For this next one, clearly, to change that into a logical statement, that'd be x is less than or equal to 5, and x is greater than or equal to negative 5. The negation will be that x is greater than 5, or that x is less than negative 5. So take the negation of each, and then the and becomes an or. Okay, next, for every real number x, there is exactly one real number y, such that the point xy lies on the graph. In other words, that the graph represents a function. So for every real number x, there exists a real number y, such that the point xy is on the graph. Now that I can't stop there because I have to say that there's exactly one number, so no other point will work. So it's also true that for every other number, if I choose some other number besides this value of y, that implies that the point xz is not on the graph. Okay, now I have to be careful about the parentheses. So this next parentheses will close that one. Then coming back here, the next parentheses will close that statement. That parentheses, and that's the statement that there is exactly one value of y that works. The value of y works and nothing else works. Okay, now for the negation, we start flipping. So there exists, so this will be the negation. There exists a real number x such that for every y, either the point xy is not on the graph, or there exists a number r such that, okay, now this is in the form p implies q, so the negation would be p and not q, so p and not q, and not this would be g of xz, so the not goes away. So there exists an x such that for every y, either the point xy is not on the graph, or it might be on the graph, but then there'd be some other point that is on that's not equal to z, which is also on the graph. So that would be the negation. Okay, next. For every positive number epsilon, there is a positive number delta, so that f of x minus L absolute value is less than epsilon whenever 0 is less than x minus c less than delta. Okay, now this is the definition of the limit existing. So for every epsilon greater than 0, there exists a delta greater than 0. And when I put a there exists inside of here, the delta could depend on the epsilon, such that this happens whenever this happens. So if this happens, then this happens. So 0 less than x minus c less than delta implies that f of x minus L in absolute value is less than epsilon. Okay, now the negation. Using De Morgan's laws, there exists an epsilon greater than 0 such that for every delta greater than 0, again, this has the form p implies q, so the negation would be p and not q. And so that would be the next statement. Last statement looks quite similar. This is the definition of a limit of a sequence. So for every epsilon greater than 0, there exists an integer such that if n is little, such that, and I should be careful here, whenever little n is greater than capital N. So for every n that's greater than or equal to capital N, absolute a minus L is less than epsilon. That's one way to do it. Another way to do it, which I almost started writing and would be acceptable, for every epsilon greater than 0, there exists an n greater than or equal to n, such that if n is greater than or equal to n, that implies that a sub n minus L is less than epsilon. That's another perfectly valid way of doing it. I probably should prefer the top way because we're specifying that n is, this is true for every value of n, but the way that the problem is stated, the second way is perfectly fine. Now the negation. If I negate this statement, there exists an epsilon greater than 0, such that for every integer n can be greater than or equal to n, and a sub n minus L is greater than or equal to epsilon. So if I take it as stated here, we have that.